This is a recast of the 4,300-word piece, Convolutional Neural Networks, from Snippet AI. This article is about convolutional neural networks, CNNs, and their applications in image and video processing. Let's listen in.
The article is about convolutional neural networks, or CNNs. We'll start off by discussing what they are.
CNNs are a type of artificial neural network, frequently used in image and video processing. They have a unique architecture that is specifically designed to reduce the number of trainable parameters.
CNNs are capable of handling large amounts of data, so they're used in various domains like object recognition, face detection, natural language processing, medical imaging, and more.
To understand how CNNs work, the article discusses several concepts including convolution, pooling layers, activation functions, and weight sharing.
Convolution is a mathematical operation performed on two functions to generate a third function. It is used to extract features from images in CNNs.
Pooling layers are also used in CNNs to reduce the spatial dimensions of feature maps. Additionally, CNNs use activation functions such as ReLU to introduce non-linearity in the model.
Finally, CNN models may use dropout regularization techniques to improve performance by preventing overfitting.
CNNs have been instrumental in revolutionizing the field of computer vision and have achieved remarkable success in various tasks such as object recognition, segmentation, and detection.
These impressive results have motivated researchers to explore the application of CNNs in other domains such as natural language processing, speech recognition, and medical image analysis.
So that's a brief summary of convolutional neural networks, or CNNs. As you can see, they've become essential in image and video processing and are likely to play an even bigger role in future intelligent systems.
To get a better idea of how CNNs work, let's take a closer look at their main components. One of the key elements of CNNs is feature detection, which involves recognizing patterns and structures in an image.
That's right. Feature detection is achieved by using a series of convolutional layers that apply filters across the image to identify specific features. The extracted features are then fed into fully connected layers, which ultimately lead to classification.
Another important step in the process is dimensionality reduction. This involves transforming the high-dimensional input data into a lower-dimensional representation, which reduces the computational complexity while still retaining the salient features of the input.
CNNs are also highly memory efficient due to parameter sharing, which allows a single filter to be applied to multiple locations in the input image, resulting in a significant reduction in the number of weights that need to be stored. Additionally, CNNs often use pooling layers to reduce the spatial size of the input, further reducing memory requirements.
To further improve the accuracy and robustness of CNNs, researchers have developed a range of techniques, such as data augmentation, regularization, and transfer learning.
That's right. Data augmentation involves generating new training samples by applying random transformations to the existing ones, such as rotations and flips. This helps increase the size and diversity of the training set, which in turn prevents overfitting and enhances the model's robustness.
On the other hand, transfer learning involves using a pre-trained CNN as a starting point to solve a related task. By leveraging the knowledge learned from the pre-training, transfer learning enables faster and more efficient training.
So what sort of applications can we find for CNNs?
Well, they have been used for medical imaging, natural language processing, facial recognition, and autonomous driving. In the medical field, CNNs have been used for the detection of abnormalities in brain scans, breast cancer diagnosis, and predicting the likelihood of developing heart disease.
And in natural language processing systems that use CNNs can better understand and interpret human language, allowing for more accurate translation and sentiment analysis.
And CNNs are also used in facial recognition for security systems and for object detection in autonomous driving, where they can identify pedestrians, other vehicles, and road signs.
It looks like CNNs are poised to become even more powerful tools in the future.
One of the most important applications of CNNs is in medical imaging. Traditionally, analyzing medical images would require human expertise, which can be time-consuming and error-prone. But with CNNs, we can now automate the process of image analysis and achieve higher accuracy.
CNNs are also used in natural language processing, with impressive results in language understanding, question answering, machine translation, and sentiment analysis.
That's right. CNNs are also used in robotics to help robots recognize objects and learn tasks like grasping objects and navigating complex environments.
And all of these applications combined have numerous uses in healthcare, security, surveillance, and so much more.
That's true. However, there are still some limitations to CNNs. For instance, they require a large amount of data to train the model for certain applications, so data collection can be costly or time-consuming. And they lack the ability to make decisions based on underlying causal relationships, which can limit their usefulness in more complex applications.
Right. And the architecture of a CNN itself is complex. It has multiple interconnected layers of neurons that filter and analyze input data. Each layer carries out a specific task and has its own unique set of weights and biases. So there's more to it than meets the eye.
Absolutely. That's why it's important to understand the limitations of CNNs and the potential solutions. Overfitting is one of the biggest issues, which happens when a model is trained too well in the training set, becoming too specific and losing generalizability.
To avoid overfitting, we can use regularization techniques such as L1 or L2 regularization, dropout, and early stopping. Additionally, data augmentation can be used to increase the amount of training data and improve the model's ability to generalize to new data.
That's true. And other technologies, such as deep learning, machine learning, and natural language processing, can be used to enhance the capabilities of CNNs. For example, combining natural language processing with CNNs has allowed us to develop models that can accurately identify sentiment and recognize named entities.
Even more fascinating is the progress of architecture design using state-of-the-art technologies like three-dimensional printing, virtual and augmented reality, machine learning, and artificial intelligence. These recent technologies are changing construction practices and enabling quicker and more effective building procedures while utilizing eco-friendly materials and designs that decrease environmental impact.
Wow, that's really incredible. So as you can see, there are a lot of possibilities for CNNs, and they have the potential to revolutionize many industries. It's an exciting time in the field of computer vision and deep learning.
Absolutely. Let's talk about the incorporation of biological neural networks. This is an emerging area of study in convolutional neural network, CNN research. The idea is to replicate the structure, function, and behavior of biological neural networks in artificial ones to improve the performance and efficiency of CNNs.
Interesting. Could you tell us more about what this entails?
Sure. This could include incorporating features such as spiking neurons, dendritic processing, and synaptic plasticity into the design of CNNs. Through this process, the aim is to develop next-generation machine learning algorithms that can mimic human intelligence and cognitive abilities.
That's incredible. So with the power of CNNs comes potential risks. What are some of these?
Well, ethics and social implications are critical considerations when using convolutional neural networks. Given that CNNs are primarily used to analyze and process images and videos, there is a risk of misuse and abuse associated with their capabilities. Particularly concerning is the potential for CNNs to be used for illegal or immoral activities like deepfake creation, privacy invasion, and image manipulation.
That certainly sounds concerning. What can be done to ensure that these risks are managed?
To mitigate these negative effects, it is important to establish ethical guidelines and regulations to govern the use of CNNs and ensure that their benefits outweigh their potential for harm.
That makes sense. All right, so let's wrap up this discussion with a summary of our key points.
In summary, convolutional neural networks, CNNs, are a type of deep learning algorithm designed for analyzing visual data, such as images or videos. The application of CNNs has significantly grown in recent years with the explosion of deep learning technology. CNNs have demonstrated remarkable performance in a variety of tasks, such as object recognition, image segmentation, and speech recognition tasks. With their inherent computational architecture, CNNs have made it possible to extract high-level features from raw data without the need for complex preprocessing. The power of CNNs lies in the fact that they have a convolutional layer that can automatically learn filters and features that are necessary for the classification of images or recognition of speech signals. The application of CNNs in many fields has demonstrated their abilities in improving current technologies.